Good afternoon, everyone. It is my pleasure to welcome you all to this session. Today, we are honored to have with us an esteemed expert in the field of guidance, navigation, and control, Dr. Abhishek Ghosh Roy. So, Dr. Roy is currently serving as the manager of controls at Tata Advanced Systems Limited, where he focuses on AI driven flight navigation. His expertise in this area is grounded in extensive postdoctoral research that delved into UAV navigation and system identification with a special emphasis on autonomous operations. Throughout his illustrious career, Dr. Roy has held several pivotal leadership roles in the industry. As the Chief Technology Officer at Paras Aerospace and lead engineer at General Aeronautics, he spearheaded in the development of AI-based drone innovations, making significant contributions to the field of unmanned aerial vehicles and aerospace control systems. Dr. Roy's work bridges the critical domains of advanced research and development in artificial intelligence, UAVs, and aerospace control systems, positioning him as a leading figure in driving technological advancement in these areas. We are incredibly fortunate to have him with us today to share his insights and experiences. Please join me in giving a warm welcome to Dr. Abhishek Ghosh Roy. So I am now handing over this session to Dr. Roy so that you can start your lecture.
Thank you, Anuradhi, for the introduction. I hope I need to confirm whether I'm audible or not.
Yes,
And
yes, you are very much audible.
thanks. And a very good evening to all the participants. So thanks for patiently waiting. I know the day is long for you guys, so I'll try to keep it crisp and brief as much as possible. Just some formal introduction about the organization I'm representing. So, as Anuradhati has already mentioned, I'm from Tata Advanced Systems Limited. We are a company that provides end-to-end solution for aerospace defense sectors, and some of our leading capabilities include airborne platforms and systems. So the integrations of mission systems for both rotary and fixed wing platforms. We have developed our own mission computer and our own ground control systems, GCS, for unmanned aerial systems, for intelligence surveillance and reconnaissance platforms. Apart from that, we also have expertise in aerostructures and aero engines. So we offer a range of services, including design, engineering, machining of composites, sheet metal fabrications, and we have also precision manufacturing capabilities for aero engine components and sub-assemblies, although not the entire aero engine, but sub-assemblies, of course. And then we also have expertise in weapon sensors and C4I systems. So we integrate sensors, weapons, and cutting-edge technologies to provide platform solutions for armed triforces, for our homeland security agencies and state police forces. And we also have another division which looks after armored subsystems. So these are some of the systems which is mounted on armored vehicles. So we have developed fire control computers for Indian weapon system, including tanks. So today in my presentation, what I will try to bring into light is the challenges we are facing and dealing on a day-to-day basis. So when it comes to industry implementation of uh, swarming and path planning capabilities into these unmanned aerial platforms. So my work on Swarm UAV AI-based path planning for Tata Advanced Systems mainly looks after these issues and focuses on addressing these challenges by leveraging these advanced capabilities and technologies to enhance the efficiency and effectiveness of UAV operations. So if you allow me, I'll try to share my presentations. Although for obvious reasons, I've not been able to showcase the most critical demo aspect of it because of some IP restrictions, but I've tried to manage to squeeze in as much information as possible. Just a second, please let me know whether it is feasible or not.
Yes, the screen
Only,
is visible. Screen is
thank you.
visible.
Thanks for confirming. So the topic of my discussion today is broadly scope of optimization and control of multi-UAV coordination in complex terrain. So this looks like a lot of uh, jargons all put together, but I'll try to break it down into simpler pieces, and probably we'll be able to solve this puzzle together. So as content flows, I've tried to touch upon the applications like what I've mentioned before, intelligence, surveillance, and reconnaissance missions, where monitoring surveillance needs uh, several agents to accomplish the task cooperatively and collaboratively. Now, that inherent property, whenever we will be using multiple agents, is something which is known as cooperation. And whenever we'll be using multiple agents, designing control laws for their motion becomes extremely challenging. Now, I also try to fit in little bit of mathematical intuitive representation of how the controlling of a single agent and multiple agent looks like, although at a very superficial level. And then what are the natural ways to address this question? So we take cues from biology or nature. So whenever we'll be trying to take inspirations from something, which is also termed as synonymously called mimicking the ecology. So we've tried to incorporate how Mother Nature solved this problem of swarming into the motion planning systems. What we have done for our systems, and our systems are predominantly VTOL. So it has a capability of vertical takeoff and landing. So it takes off just like what you guys have seen helicopters or maybe some of the drones you might have seen taking pictures or videos in marriages of your friends or colleagues. So this doesn't require a runway to take off, right? So our systems, unmanned aerial platforms, basically are equipped with VTOL capabilities. Along with it, in order to increase mission effectiveness and the endurance, it has fixed wing capabilities as well. So these are sort of like a hybrid between a helicopter and a fixed wing normal classical aircraft configurations. So quadcopter dynamics is a very simple form of representation of this kind of VTOL capabilities. So I've tried to touch a little bit of quadcopter dynamics as well, and few of the approaches what we take, and we not only always resort to using cues and inspiration from Mother Nature, we also sometimes resort to more classical graph theoretic approaches as well. So little bit of simulation results from graph theoretic approach as well. So few terminologies to begin with, we need to be familiar with. So optimal path planning, what does it basically mean? So path planning is a critical aspect for unmanned aerial vehicles to uh, efficiently accomplish their missions by determining most effective routes and to optimize other mission critical aspects like increasing the endurance as much as possible, squeezing in the last drop or last ounce of energy from its powertrain, power sources like batteries. It could be batteries, it could be even powered by an IC engine. And then there's an aspect of grid-based approaches. So grid-based path planning generally divides this area into a graph-like representation into grids, and it facilitates easier navigation for UAVs, ensuring efficient routing. And the graph-based techniques. These are more of a classical nature. And the challenges what we face on a day-to-day basis are in terms of communication. So two important aspects whenever somebody is talking about unmanned aerial platforms is two matrices, basically. One is called a communication radius. The other one is called a sensing radius. So as can be seen from this, so both plays a very important role. So communication range determines if there can be an analogy given to this is how far you can basically communicate. So in an unknown terrain, uh, the louder you shout, the more distance you are supposed to cover. But the louder you shout, you tend to expend the most amount of energy in the process as well. So our intention is to serve the critical mission parameters, solve them in a way which is most optimal for that particular mission criteria. So maybe we can afford to have a near infinite or theoretically infinite radius by incorporating a very big FM transmitter or narrowband transmitter on top of an unmanned aerial vehicle. But whenever it comes to this kind of aerial systems, both weight and energy budgeting is a very, very important criteria. So we'll have to preserve the maximum amount of battery power for any kind of mission critical scenarios. And also we'll have to reduce the weight for the obvious reason, right? So it's a chicken and egg problem of some sorts. So if you tend to increase weight, you end up using more power resources in order to keep it afloat. So these important considerations are one of them is communication protocols, because in today's scenario of modern warfare, there are a lot of enemy activities which mainly focuses on intercepting the communication between your ground control station and the airborne platform. And it doesn't end there. So if you want to operate in an enemy territory, there are chances that they would to some extent inevitably turn off their GNSS, Global Navigation Satellite System constellation, and you won't be able to locate your surroundings. You won't be able to identify your positions based on GNSS, or in simpler terms, GPS based coordinates. And there are algorithms which are called spoofing algorithms, which mimic the protocols which are used to communicate between the brain of those airborne systems, which is called a flight controller, and the muscles of those airborne systems, which is called actuator. So the communication between brain and a muscle is done using certain protocols. In aviation, we use somewhat like, because it's a very niche industry, somewhat like uh, CAN bus or CAN 2 protocol, which is very, very widely used in uh, automobile industries. But it's not entirely similar. But if you end up using this kind of well-known public domain communication protocols in combat scenarios, you end up losing the communication between your brain and your muscle. So you have to be prepared with this sort of scenarios where spoofing algorithms will be thrown at you, and you need to have a communication protocol of your own IPs. And then there are techniques for coordinations. Different techniques can be used to enhance coordinations between UAVs. More specifically, we'll be dealing with and taking a look at these coordination techniques. So if you want to discuss about multiple UV coordinations, the term which is most commonly used, it's called swarm of unmanned aerial vehicles, or UAVs. So swarm generally, the term came about from some of the typical animal or insect behaviors in nature. So probably uh, most of you would be familiar with this kind of configurations of insects. These are called cicada insects, and these are found in northeast uh, of US. So they generally forage in every once in a decade. So during their foraging, so they kind of display this sort of a typical behavior, and this is like swarming or schooling of fish. How fishes try to find out food locations and the presence of predators, and maybe cues or instructions from their team leaders. Okay, so this is a typical behavior which is observed in nature. And this is some wildebeests in Africa. So they also tend to showcase similar behavior. And this is a herd of cows or farm animals. So they generally tend to showcase those. So what scientists got intrigued with is the behavioral pattern of all this swarm activities, which takes place very commonly. I mean, it's a day-to-day affair if you talk about Mother Nature. And what they try to find out is a mathematical model which represents this swarm behavior in its most fundamental form. So, what they tried to do initially was to color mark bees swarming around a beehive and then track it with a motion capture system, and then try to find out of what each and every member of that bee colony is doing, and somehow put together a mathematical framework which will replicate the behavior. So, in some such endeavors, multiple theories have come about. One of the most popular and well used in industry of such derivations is something which is known as cousin model. So Cousin and team proposed this algorithm in year 2002. So it's very well documented in that paper. So it's called Collective Memory and Spatial Sorting in Animal Groups. It's published in Journal of Theoretical Biology. So what it basically means are three fundamental thumb rules. So, which I mean, this is something which inevitably every member of the swarm follows. So, this fundamental thumb rules are broken down into three different distances. So, as you can see here in the left-hand side top corner, so there is a contour plot which has a central circle, three concentric circles. The central circle in an pinkish shade corresponds to the zone of repulsion. And then the middle zone, middle spherical zone in bluish hue corresponds to something which is known as zone of orientation. And the outermost greenish circle or sphere in a 3D sense corresponds to zone of attraction. So what does it basically do? So we can see all this mathematical relationships which has been modeled on those behaviors. What it basically does is, so let me play the video to make this a little more understandable for everyone involved. So what it basically tries to do is every member of the particular herd or a swarm or a school tries to maintain a safe distance or tries to satisfy a condition which is called collision avoidance between its nearest neighbors. So that particular radius, it's called the zone of repulsion, which is represented by ZR. And once that condition is satisfied, next priority is given to ZO, which is zone of orientation. So what it tries to do is, once it has satisfied that it's not colliding with its nearest neighbors, it tries to orient itself with the most amount of neighbors it can sense. So here again, as I've mentioned before, the sensing radius and the communication radius plays a very important role. So as far as it can sense, based on that particular environment data, it takes a decision to orient itself in the along with the mode of the population which is available at that instant. So that is ZO. And ZA is a very intuitive term. So one can think of in a way like whenever we'll be in a crowd, will always not in a crowd, we will be in a company of multiple friends. Let's say we've gone out for a trekking or something. So everyone will always focus on something which is called the uh, the basic what do you call this, the basic intention of everyone involved in that group will be not to fall behind, right? Not to come out of that particular group. So there needs to be a mathematical representation which mimics that kind of behaviorism. So this is called zone of attraction. So once it goes beyond a certain radius of that particular swarm, there will be an attractive component which will be attributed to this, which will make sure that no member of that swarm gets left behind in the process. So the following slides, which I'll be showing, takes this cuisine model's simplest approach and tries to modify bits and pieces of this cuisine model, and those bits and pieces fits. I mean, this is nothing like a panacea, one medicine for all diseases. So this is like for a certain category of airborne vehicle, certain approach might work wonders, while the other might fall flat on its face. So here, what you can see in the cruising model, the vehicles which are very, very highly dynamic and maneuverable in nature, cruising model in its purest form are generally adopted. Now there are vehicles like quadcopters or normal drones, which have higher holonomic capabilities and which are not that dynamic in terms of maneuverability. Those are not the suitable candidates for applying these models in its purest form. So there are multiple variations and multiple small modifications in this. A psychomimetic model is one such modification. See here, what we try to do is on the movement of the swarm itself, we try to bias. So how does that bias work basically? So a physiomimetic model mimics the working principle of some of the most common artificial physical forces like electrostatic attraction or gravity for that matter. So what it basically makes sure is it's the same way a matter gets attracted to a heavier matter, or same charges repel each other. So an airborne aerial platform gets repelled from its nearby obstacles and gets attracted towards the goal, the mission goal, or the global optima for that matter. So the here, as you can see, so G is sort of like an electrostatic constant or a gravity constant, and then mj corresponds to the mass of those parameters based on which it will be biased, and r to the raised to the power of p mimics the artificial, because as a special case, if you consider p is equals to 2, then it will model all the spherical forces in nature. And there is another biasing strategy which is adopted in industry, which is called pairwise interaction model. So here the idea is very, very simple, and it works wonders for platforms like quadcopters or hexcopters, which are not extremely maneuverable in nature and which doesn't involve very, very complicated fluid dynamics into it. So the idea is one particular agent which is acting to some extent like a leader of a swarm is responsible for influencing one. So this works in a pairwise mode. So one of its swarm members. So what it tries to do is that aligns the next swarm member along with its direction. So once it is done, then it focuses on the next. Now, if you have done it enough number of times in a particular swarm, what you have basically ended up doing is align the entire swarm in towards a common goal. So this is how basically this pairwise interaction topological model works. Now, how do you control a swarm? Basically, the strategies to control a swarm is uh, a little involved. So you can influence a swarm by using rewards or by using penalties. So in terms of rewards, you can think of it to be somewhat analogous to a food source. Maybe there exists something which attracts those swarm towards it, and the incentive towards reaching it is basically it will be fed, or the chances of survival of that particular um, agent for the next generation will be higher. That is one model. The other model is by penalty. So penalty is given by certain agents, specialized agents in a swarm, which are called predator. So the analogy, what you can see in this presentation, is a herd of sheep being directed towards pasture land by a sheepdog. Or even you can think of something as similar to a leader. So leader also plays a role to some extent similar to the predators, but the principle of operation is not exactly identical, and it has a capability to influence agents. So the sheep behavior, or you can think of it in generic terms as the swarm behavior, is said to be attracted by a neighbor, to be repelled by a neighbor, and repelled by a shepherd. In this case, it was a sheepdog. And the shepherd behavior would be something like shepherd, by the way, is also a specialized member of the same swarm to stay behind the herd so that no sheep is left out, and then go behind the ship if it is left out to collect it back in the swarm. So that is shown in this figure. Now, there was multiple researches conducted in terms of finding out what kind of leader-based approaches are most effective in order to control something which is not centrally controlled. The way we say the term centrally controlled is not exactly succinctly realizable in terms of data scientist perspective. But if you think of it from a GNC, a guidance navigation control point of view, so you can achieve a swarm or a coordinated movement by feeding each and every member of that swarm with a proper mission plan that doesn't require any kind of communication in between drones, that doesn't require any kind of sensors being equipped into the drones. So both the swarm members can be deaf and blind, but still be able to operate in a collaborative manner. That is what is basically done during light shows of drones. But this is not that case. In here, every member of the swarm has its own decision-making capability. So this is somewhat uh, replicating what we see in nature. So, and what the leaders basically do is try to achieve a pattern in this swarm, which satisfies a common goal for the swarm, making sure that each and every individual also optimizes its own choices. Now, there is a concept which is called careless leader. So, careless leader is someone who always only looks at the goal. Okay, it doesn't have any communication between its surrounding neighbors, or it doesn't try to take into account what its nearby swarm members are doing. it only focuses on, completely biased towards going towards or achieving its goal. And there is another model which is called effective leadership model. So it balances between these two things. So although getting towards goal is also very important, but it cannot deprioritize the necessity of cohesive approach. So what it basically does is it takes a probability, okay, with which it biases itself toward goal, and one minus that exact same probability attributes towards the interaction between its nearby swarm members. So as you can see, this literatures are mentioned, and we've conducted few experiments in order to find out the placement of leaders, where exactly if you end up having a leader based approach. So this is again not fully distributed architecture what we are talking about. In a distributed architecture, a leader will be dynamically chosen from the swarm itself, but here what we are trying to do is to assign this specialized responsibilities to certain members of the swarm. And what we end up doing is we chosen the most simplest model of leaders, and we place them at different locations. So strategically, the leaders can be placed at front of the swarm, and somewhere towards the centroid of the swarm, and on the periphery of the swarm. And what we, although this was not exactly what we are expecting, but what we ended up finding is the middle position or the middle location for this kind of careless leaders are the most effective locations, because what we they ended up doing is, in addition to achieving the goal location, they also made sure that no member of the swarm were left out. Okay, so this is some of our findings. And so as we are talking about level 4 autonomy, where a human is not present and the drones are the only decision making agents in that particular thing. But there is a NATO verdict on application of artificial intelligence based systems, which asks for a human decision maker to take the final call when it comes to hit or kill kind of mission. So what we had to, although we were not in favor of it, but what we had to end up doing is a human leader interaction model for the certification of that airborne platform. Okay, so human in the loop adds another level of complexity in that entire mix. So what it does, it increases the operator effort with an order of another order. So as you can see, this mathematical model is also depictive of this complexity, add-on complexity. But again, as the regulations are very strict, so we'll have to we had to end up doing it. So some of the topics which I've touched upon are somewhat like this, and I'll quickly try to show that how it's basically done. So once you have ended up mathematically simulating a swarm environment, now how do you make sure that that and same exact same strategies what you are proposing would be effective in the battlefield? So basically, what is the intention of an unmanned aerial platform? The whole point of having an unmanned platform is to be able to reduce an operator's cognitive load. Now, instead of a single platform, if you're talking about a swarm, that adds another, as I've shown, another order of complexity in that entire mix. So we've used several simulation systems, and we've tried to model the cognitive complexities, the cognitive loads, which it ends up adding to that entire process. And this is what we found out. So first of all, if you want to model cognitive load, you have to first consider or first understand what are the tools or for an effective navigation. So for a human operator to take uh, informed decision in a combat environment, he needs to be equipped with the full map of the battleground. That's number one. Now he can't always remember the full map in it in his limited cognitive capability. So he'll have to only focus on a certain specific area of that map where that operation needs to be surgically carried out. So that's called a mini map. And there are several perspectives which are available for a human operator. So the perspectives are categorized as first person perspective, wherein the drone which is carrying out that mission is itself equipped with an FPV, first person view camera. And there is something which is called third person perspective, where a traffic camera, or maybe a camera mounted on a low Earth orbiting satellite, or maybe on a different member of that same swarm, is equipped with that. The reason, because this question might come very naturally, what exactly is the need of this third person perspective? It's because of the fact what I've mentioned right at the beginning of this discussion, that every unmanned aerial platform suffers from something which is called a limited weight and limited resource budget. So we can't equip every drone with all the payloads possible. So maybe some of them will be specialized for carrying explosives. Some of them will be specialized for carrying ground penetrating radars. Some of them will be equipped with thermal cameras, and only very few of them will be equipped with EO cameras, electro-optic or RGB cameras, as we call them. So this first-person perspective is a luxury. If we can have it, it's all, and nothing can beat that. But otherwise, we'll end up resorting to third-person perspective. And this the right bottom image showcases that entire battlegrounds selective section of this and the takeoff region. So this questions came up during that process of development. So whenever we are trying to mathematically find out the cognitive load and cognitive load reduction by implementing these strategies, so why don't we do that on a 2D screen instead of going full on as a virtual augmented reality? So in order to justify our claims, what we had to do is to mathematically model this cognitive penalties, and we formulated four different scenarios. So in the simple terms, the scenarios are categorized as follows. So this 2D with no assets. Assets are those informations which are available to a human operator during a combat mission. And then there is 2D with all the assets. So absence of information is one thing. Overload of information is also another complexity. So similar way, what we've done is for VR also, we've done 3D with no assets and 3D with all assets. And what we ended up finding, I'll show you the results. So as a metric for comparison of this cognitive load, so we have used NASA's TLX task load survey form. So it's basically a set of questions, a questionnaire that every operator had to fill, and based on that, and these questions had different weightages, and this is something which is very standardized, and we all the aviation industries use it on a day-to-day basis for monitoring operator loads. And then another important factor was the time taken by the participants, and then percentage of area covered. So the exploration aspect of it, exploration efficiency, which is a ratio of time taken and the area covered by the participant, and then completion of percentage. So how many of them are basically untrained? We've also categorized them in groups of untrained operators and trained operators. So we've found there is a market difference between how an untrained operator operates and a trained operator operates, and the asset usage. So how to optimize the asset usages during a combat scenario. So this is the result. So cognitively speaking, experiment 2 was much more demanding compared to experiment 1. And what you can see is the mean and the standard deviation of those KLX NASA matrices. So experiment 1 mean lies way below experiment 2 mean, and the scatter and the standard deviations of those experiments were on somewhat a similar scale. So it ranges from both experienced to inexperienced operators. Now, based on NASA TLX, as you can see on your left side, we've plotted all the 2D with all assets, the cognitive load, 2D with no asset, 3D with all assets, and the circular plots, what you can see are the outliers. So we've not considered them while calculating. So we've considered only those data which are clustered, and we've chosen a certain cluster center for carrying out these calculations, and 3D with no assets. And on your right, you can see. So this is both experiment 1 and experiment 2. So based on their performances, what you can see is this guys are grouped together. And experiment 2 is always, of course, undoubtedly more demanding, but at certain cases, so if you can compare the case where with 3D no assets for experiment 1 and how it compares with 2D no asset of experiment 2, you can see that there is a very, very astonishing result which comes out of this experiment. So the results can be concluded somewhat like significant difference between the cognitive load experienced during completion of experiment 1 and 2, with a higher load in second experiment that is inevitable, and we didn't have to come up with any further justification for measuring the cognitive load. And inexperienced participants found the 2D no asset load least demanding in the first experiment. In the second experiment, after gaining experience, they faced difficulties in 2D no asset, and significant differences between 2D all assets and 2D no asset. Same for 2D all asset and 3D all assets. Now, based on time taken, so earlier one was a comparison metric based on the cognitive load, and this is on time taken. So as you can see, so the time taken to complete experiment 1, it's to some extent similar to the time taken to complete experiment 2, although the cognitive load was hugely different from each other. But again, this is something what we've found out. And there are some outliers in this, but again, the mean and the standard deviation tells the story. Now, with 2D no assets, as you can see, comparison of normalized time taken by the experiments. So this is normalized time versus the experiment ID, and the other one is normalized time taken by the both the experiments 1 and 2. So the results can be adjusted in as follows. No significant differences between experiment scenarios. Time taken in second is generally less than first. Higher variance in 3D scenarios, and 2D no asset scenarios had the worst performance in second experiment. And this is based on the amount of area covered, the exploration aspect. So you can see the same approach we've taken, the systematic approach of finding out and mathematically explaining these things. And what we found out is no significant difference between experiments or scenarios, and higher variance in all 3D asset scenarios. So the performance of an experienced operator and an inexperienced operator is markedly different. The 3D scenarios in the first experiment showed higher variances. Now, based on exploration efficiency, so as you can see, experiment 1 and experiment 2, and this is again the same approach, and the results show no significant difference between these experiments. The significant difference between 2D scenarios and 3D scenarios can be observed. It clearly shows augmented virtual reality is the right approach towards solving this problem, or at least training the operators. So this is on percentage of completion. This is again somewhat similar. And what we've been able to showcase is 70% completion in first experiment and 75 in second, higher completion rates in 3D scenarios, and 100% completion in 3D scenarios during second experiment. So this was somewhat like an irrefutable proof in favor of opting for augmented virtual reality and asset usage perspective. So this is not entirely relevant for this discussion, but again, one can just try to look at from a researcher's mind. So what we found out is third person perspectives are preferred basically, and increase in use of fixed perspectives in all 3D assets. So this is asset usage full map. This is on the templation used count. And as a conclusion, VR environment showed potential for improved human-swarm interaction. 3D scenarios generally led to better performance for operators and completion rates. Participants adopted to VR features, and further research were needed. So basically, end of the story is we got a little bit of momentum in this direction through this exercise. Now we has not been able to discuss directly looking at the equations because of obvious IP infringement issues. So I've tried to find out the extract of those mathematical equations and put them in words. So basically, what it does is there is a challenge for task allocation. So how effectively, with a limited sensor and communication budget, so you effectively allocate task to the swarm. That was one important aspect what we had to deal with. And then we proposed several techniques for that. Sequential auction scheme is just one of them. And then validation and decision making process. So this targets will be validated using neighbors' knowledge, and agents decided to go for an auction to or forfeit those targets. And then we carried out detailed simulation and comparison with those simply distributed auctions and greedy strategies. And this military applications, as you can well appreciate and understand, so this is basically meant for multiple applications. So one of them is intelligence, surveillance, and reconnaissance. The other one would be something which is somewhat similar to loitering munitions. So you can carry out a very precise airborne attack using this avionic platforms. So they have certain limited capabilities in terms of stealth and payload as well. And the UAV cooperation. So teams they required for complex tasks. So certain members were crucial for completion of certain tasks, and there was a need for autonomous decision making in spite of having human in the loop. And we've also been able to compare the pros and cons of centralized versus decentralized task allocation scheme. And with limited communication and sensor ranges, we've tried to find out what are the challenges. So uh, this is somewhat like very, very schemed and very, very diluted form of the task allocation algorithm. So what you can see is one UAV is assigned to one target. So example, A1 of that UAV swarm group So the first member may be assigned to task one, A2 may be assigned to task three, A3 may be assigned for task two based on what kind of optical or what kind of explosive payloads they're carrying and what are those corresponding tasks. So you can think of it in terms of a weighted graph and how we solve a traveling salesman problem for a weighted graph. It's to some extent similar to that approach. And then limitations of traditional schemes. So we've been able to showcase the classical techniques, and some of them actually literally falls flat in while it comes to applications of this nature. Then a sequential auction approach. So A1 can bid for both T2 and T3. So this is somewhat different from traditional task allocation. Sequential approach asks for every member to bid. So they generate a matrix of n cross m dimensions, and wherein all those auction elements will be populated and based off the determinant of those matrices. And so each and every task will be dynamically allocated to those agents. And communication constraint. So we've also been able to model the communication constraints into our simulation. So this is somewhat like a problem overview for this. The NUAVs performing tasks to search and destroy. So, and task allocations are done using assign agent to target MJ and constraints and assumptions. So when it comes to constraints and assumptions, we basically deal with two kinds of constraints. One is called constraint, which comes from the concept of holonomicity, so non-holonomic constraint. And the second one is called kinodynamic constraints, which comes from both kinematics and dynamics of those vehicles. And then cooperation and mechanism. So mission objectives, task allocations, communication constraints, cooperation between UAVs. Simple auction scheme is agent acts as an auctioneer, other UAVs bid for the target, auctioneer announces the winner. So this deals with the problem of limited communication radius. So what ends up happening is multiple UAVs auctioning for the same target, the bidding agent receiving the same target, auctioning information from different auctioneers, bidding UAVs receiving auction requests from several different auctioneers. And then the simple auction scheme gets modified. An agent acts as an auctioneer, other UAVs bid for the target. So this is basically the crux of the problem what we deal with when it comes to multi-UAV cooperation and swarming. Now, a little bit before I showcase some of the simulation results, a little bit of detour regarding quadcopter and how it is basically modeled as a point mass or a distributed mass mathematics, and how we derive the kinematics and dynamics from a quadcopter mathematically. So basically, when it comes to mathematical representations, so finally, the representation will either fall into the category of Eulerian representations or maybe in terms of quaternion representations. So for the sake of simplicity, we have kept it strictly towards Eulerian representations. So here, the force equations and moment equations are as follows. So as you can see, each and every propeller of this particular UAV rotates with a certain angular velocity. So these are represented by green circular arrow, W1, W2, W3, and W4. So a fun trivia would be why exactly it rotates in different directions. Because as you can see, if W1 is rotating in a counterclockwise direction, W2 is rotating in a clockwise direction. So from the basic fundamental knowledge of mechanics, one can argue that the resultant momentum of those generally what comes out as a as a byproduct of those rotations are represented with this blue circular arrows, what you can see as M1, M2, M3, and M4. So this is a reaction force of and force analog. So with every force, there is a reaction force. So with every momentum, there is a reaction momentum. So this momentum comes as a result of this omega, or the angular velocities of this rotors. So if you consider the direction of rotation of this rotors as W1, the resultant momentum will be in opposite direction, which is given by this blue circular arrow in clockwise direction. Same for all other rotors. So a force balance and a moment balance equation in the body frame of this vehicle. So again, here the frames of reference plays a very dominant role when it comes to mathematically representing an airborne platforms. So resultant force would look somewhat like this. So in absence of any acceleration, if you are talking about an equilibrium, then F would be equal to the sum of all those forces produced by these rotors, F1, F2, F3, and F4 summed. But if there is an non-symmetry in the equilibrium, there will be, as a result of unbalanced forces, there will be an acceleration, and this acceleration is represented by mg, and this is towards, as we are only considering vertical forces, so this is towards the z-axis, which is given by a3. So this will be the acceleration will be as a3. So this is what basically the resultant force would look like. Same for the resultant moment. So the length of the arms of each side of this rotorcraft are given by a R1 to R4, and the corresponding forces. So if you try to multiply those moment arms along with the forces, you end up having the moment. So the resultant of those moments would look somewhat like this second equation, and they are balanced by the counterclockwise and gyro moment of capital M1, capital M2, capital M3, and capital M4. So this is just some fundamentals, and this is a textbook material basically. So if you recall fluid dynamics, and maybe some of you have background or research background in it, so what we can easily conclude is the force is directly proportional to the square of the angular velocity of the rotors. And same goes for the moment created by this. So the graphs would be correspondingly looking like this. But basically, if quadcopter is trying to stay afloat in equilibrium, the force it has to produce as a very minimum or basic requirement is its own body weight, which is nothing but mg. So if it gets shared into four different rotors, so each one would have to produce something which is mg divided by 4. So in the same way, what we can conclude, just take a look at the previous equation. So a more mathematically sound form of this previous equation would look somewhat like this. So F is given by sum of all forces and by the unbalanced acceleration, and then the net moment is produced, which is sum of all the forces produced by this propellers and the gyro moments. Here you can see two different frames of reference. One is an inertial frame of reference, which is basically the world frame and doesn't have any acceleration. And the other one is a body frame, which has its own accelerations and a rotational acceleration, both and linear and rotational accelerations. And this forgot to mention, so this proportionality constants are given for both for force and moments are given by Kf and Km, which again depends on the materials with which those blades are made. So for a polypropylene material, the corresponding Kf would be different if you compare it with a carbon fiber based propeller construction. Then the geometry of those propellers, like angular twists, geometric twists, diameter, width, and then pitch of those propellers, the air viscosity surrounding it. So viscosity is again another function of altitude, temperature, density. So all those plays a very critical role in forming this proportionality constants. So for a given area and for a certain time, one can consider those to be parameters for the sake of simplicity. And the Newton-Euler model for this. So I don't know whether it will be relevant, but I thought it's important nonetheless. So that's why I kept it in this presentation, because one has to also understand, in order to solve problems of multi-UV cooperation, we'll have to deal with the complex dynamics of those airborne platforms. So that's the precise reason why I thought of having this particular thing in this presentation. So this angular velocity in body frame. So basically, as humans, we are very limited, and in real life, we can't always rely on a motion capture system or some kind of third party observing mechanisms which will give us the attitude. So attitude means the angular orientation in space in real time of those vehicles. So that's why we end up using onboard sensors. So this is called automatic heading and reference system, AHRS. So what we actually use are set of sensors which are called inertial measurement sensors or inertial navigation sensors. So those give us data on the angular velocities and the accelerations, linear, both linear and angular. So these are called gyroscopic sensors and accelerometers and magnetic heading sensors. So all of those sensors are basically on board that airborne aerial platform. So the data which comes out of it as a result is on the body frame. And but the way we explain motion, velocity, distances are all based on a third person's view perspective. So basically, if you want to denote the velocity of a vehicle or the descent rate of a vehicle or an ascent rate of a vehicle, you'll always refer to the world frame if you want to actually denote it. Nobody actually cares for the body frame analysis in that respect. But those sensors, our eyes and ears, are on the body frame. So we've to transform these equations into inertial frames, and these are the corresponding equations for it. And and you can see it's evident that we'll basically have to form it just like a control problem, where we have idea about the system, we have a desired output. In this case, it would be a desired trajectory, but we have to find out set of inputs or set of U's which will end up having or end up influencing the system, so that influence can track that desired output. That's basically is the control problem. So this derivation goes on like this. So if you end up simplifying, you get a better mathematically aesthetic representation for U2. And the control problem, basically, if you are only focusing on altitude control, you can even simplify it to the extremes of a second order system. So the control problem would look somewhat like this, where state input, plant model, and everything is known. And then the general approach would be to find out an error equation. So error is nothing but the desired minus observed. What you can see here is ET is found out as desired minus observed. And then we have to find out a cost function. In this case, we try to find out a cost function so that the error is almost always guaranteed to asymptotically approach zero. So this is a very, very popular and well accepted industrial method, which is also called PD control. So proportional and derivative controls. So this is the objective function or a cost function for a PD controller. And whereas you can see there is a velocity term with the first order derivative of that error metric, and there is a proportional term. Along with it, there is a feed forward term. So we make use of the a priori knowledges of the desired trajectory, and we try to force feed this with the prior information of the desired trajectory. So in most of the practical cases, this solves the problem. In some of the instances where we have not accurately modeled the systems, so system suffers from something which is called modeling error. Maybe in this simplest form of example, we can consider it as the mass is unknown, or maybe some other mass inertia properties, maybe moment of inertia at a certain angle is unknown or estimated not so accurately. So in such scenarios, we need a term in this cost function which will over time accumulate and negate the difference, and which will make sure that our error function asymptotically approaches zero. So in such scenarios, we'll use PID controllers. So it's very common. So I just kept for the sake of it. And this would be a high-level picture of the controllers, which is deployed in a multi-copter system. So be it quad, be it hex configuration, be it counter-rotating helicopter-like platform. So all of them basically adheres to the same high-level controller architecture. So there is something which is called a trajectory planner, which comes up with a desired trajectory in real time. So it's on not only the desired trajectory, so it has to perform or feed this desired trajectory information at a certain rate to the inner controllers. So inner controllers are mostly responsible for making sure that your UAV and manned aerial vehicle is oriented in the desired states. So it's called an attitude controller. So it tries to have those informations from something which is called position controller. So this is a cascaded controller architecture. And this inner loop, what you can also call the attitude controller, has to run at a much faster pace compared to the outer loop controllers. And basically, this is what we deal with on a day-to-day basis, because the sensors which are on board, as I've mentioned, and are feeding those informations, state informations. So P dot T, Q dot T, R dot T are respectively roll, pitch, and yaw. So angular velocities. So this sensors tend to perform at a much faster rate. So if we want to use it to its highest efficiency, we have to have a controller which is running at a much more faster rate compared to the decision making processes or the desired trajectory informations which comes as an output of this trajectory planner. So they basically rely on sensor informations from systems like radar, or maybe lidar, 360 lidar, or maybe GNSS based positioning systems. So this form of sensors suffers from a lot of lags, and these are basically non-real time estimated outputs. So they have to rely on this kind of sensor values, and that's why what we have tried to do is to segregate these two aspects of the controller. So one which is most dealing with most flight critical aspects and maintaining the flight's stability in real time. So that has a higher priority and a higher speed of loop execution. And the one which is sort of like less safety critical, although it's mission critical, but less safety critical, that is given a lower probability because of the, again, obvious reason of sensor limitations. So next topic, what we'll be discussing is called rapidly exploring random trees. So here, what we've tried to do is we've modeled those agents mathematically using those equations I've shown in previous slides, and we've tried to find out how effectively or efficiently they can find out um, uh, and locate their goal or destination directions, or carry out their missions most effectively without having a complete knowledge of the global map. So there are multiple variants of this approach, which is as shown here. It's called vanilla, rapidly exploring random trees. Then there is an approach of single oriented trees, bidirectional trees, and there is an also concept of forests where we have multiple agents thrown at the mix right at the same time. And we also have to deal with the constraints which is imposed by the non-holonomic and kinodynamic constraints. So if we take a look at how this method works, we'll have to be familiar with something which is called Voronoi diagram. So this Voronoi diagram is nothing but a discrete set of regions or set of points, and for each such point we decompose the space around it into some zones or some regions of influence. So the property, geometrical property, what we have to satisfy in order to decompose this space into a finite number of regions of influence is that we have to make sure that any point in that particular region is closer. So you can take a Euclidean distance, you can take some other form of distance metric, but whatever uh, distance metric you are choosing, based on that, this particular point in that particular region has to be closest to that point than any other point in that vicinity. So as you can see on your left diagram, so we have initiated this entire diagram with this many points, and this has ended up dividing the region of influences into this finite number of region of influences. Now, the as I've shown, there are multiple variants of this random tree approach. So the most crude or most pure form of random tree approach is something which doesn't have any bias. So how do you explain bias in the context of random tree? So bias is nothing but an incentive for achieving a certain goal. So something can be biased towards exploration or exploring new or more unexplored areas. Something can be biased towards goal. Something can be biased towards avoiding collision. Something can be biased towards making sure that we complete that entire mission in the most optimal, energy efficient way possible. So there are a lot of ways one can bias random walk, and this depends on this nearest neighbors. So what we've ended up doing is we use the Voronoi weights as biases for this random trees to generate. So you can take a look at this simulation quickly. So here, as you can see, a modified form of RRT star is chosen. So we are adding 10 more points into this simulations, and as you can see, it's exploring the area in an effective way, and will keep on increasing it. Now we are about to add 100 points. As you can see, most of these areas are covered, but the thing is that the path what it found out, one can see and conclude that it's not the most optimal path for sure. So there are multiple variants or multiple smart ways to deal with this problem, but this is guaranteed that exponentially, as we keep on increasing the number of points, and as the number of agents tends towards infinity, it would finally find an optimal path. So that is mathematically convergent. Now, if we try to look at the path length, what it's generating, just something to remember that it doesn't have any exploration bias. So exploration bias is zero. So basically, it's fully biased towards your goal. Now, this is a complete contrast to another alternative approach, which is called probabilistic roadmap method. So here, the exploration takes the foreground, and the optimality or convergence of those is not entirely mathematically guaranteed. So that's the reason more popular and industry adopted method tends towards RT. So just bear with me. I'll just like to showcase few of the aspects when we increase the exploration bias. As you can see, very smooth trajectory has been formed. Now, this is a random tree. A stark contrast from rapidly expanding random tree and a random tree is that in a random tree method, nothing is basically governed by a dynamics. So you flip a coin and decide whether you want to go right or left. So based on that, your exploration gets the maximum hit in this kind of strategies. But with RT modified, so the exploration is given the force hit, and this is sparse. So blue sections represent the obstacles, and the outer perimeter of this showcases the geofence of this. We keep adding number of nodes. As you can see, as the number of node increases, it's guaranteed that at a certain point of time, we'll always end up having the solution. Now, what we try to do is try to force feed some a priori information about the obstacle and also increase the exploration bias. So here, so exploration bias would also have equal priority compared to the goal bias. So with the same probability, it will generate another node towards the goal and also towards unexplored spaces. So 50% of the time, it will be motivated by the goal location, and rest 50 it will be focusing on exploring new spaces. So with that modification, as you can see, so Uh, Conclusion, we can say single parameter um, is normally responsible. So these are the pros aspect of graphical techniques. So this is only limited number of parameters. In this case, it's a single parameter that controls the output. It's a balance between greedy and exploration based techniques, and it's very easy and computationally efficient to implement. But it suffers from metric sensitivity, and then its nearest neighbors are the ones which decides the efficiency, and the rate of convergence is mathematically unknown. So you can't guarantee a certain rate of convergence in this. So this is something I wanted to show just at the end of this presentation. So it's a human swarm interaction in virtual reality. So for an operator, as I've mentioned in my previous slides, whenever we are be measuring the cognitive load, so for an operator with all the assets given in, so a human swarm interaction, it would look somewhat like this. And this is again a very limited of one of the swarm simulations. And this is one of the gazebo based simulations. All of these are well documented in open source platforms. So I'm done with the presentation. If anyone has any question, please feel free to ask. I just would like to highlight that the key issues for accepting this proposal for this was for me to invite collaborative solutions that would help us overcome these obstacles what we are facing on a day-to-day basis. So if anyone has any innovative ideas in terms of collaborating with industry and coming up with solutions, because at the end of the day, what we plan on achieving is a common goal of serving our nation by equipping our tri services with this form of cutting edge technological advantages. So if anyone is of you, the participants is interested in collaboration, I will feel that this presentation has been to some extent productive. So please feel free to ask questions. Presentation wise, I'm done.
Thank you, Dr. Abhishek. It is a nice presentation, and we are so much delighted to have you in our session. So I am just asking the participants whether they have any kind of queries. You have great opportunity to have Dr. Abhishek with us, and you can put your queries or your concerns or your any kind of thoughts, before him. Over to you, participants. Is there any queries you can ask? Feel free to ask, Dr. Abhishek. Actually, it is our sincere gratitude, Dr. Abhishek, that your profound insights and expertise have truly enlightened us and offering a clear understanding of the challenges and opportunities of the UAV coordination, what you have discussed with all of us. So, actually, your deep insights into the complexities of UAV coordinations and optimizations also have not only expanded our understanding, but have also inspired us to explore new frontiers in this domain. You have also, shared with us that you are very much eager to have a collaboration itself if anyone wants to. So it is a great opportunity, and we are immensely grateful for the time and effort you dedicated to sharing your knowledge, which will undoubtedly inspire and guide us in our future interviews. So thank you once again, and we hope to continue this journey of leading and collaboration with you. This is what I feel from my side. So, and for
Thank
participants
you.
also,
Thank you so much for giving me this opportunity. Thanks.
sure, sure. We are also very much delighted to have you in your such a busy schedule that you can make us, and we are truly, truly, grateful for this. And for dear participants, so we are actually closing our today's both the sessions. So for you, actually, the first session feedback form is already shared, and the second feedback form will be shared very soon. So you just fill up and submit all the feedback forms by tonight, and please make yourself attended in every session so that we can be able to upload the attendance of all the participants of 115 participants. In fact, we have in our ATAL FDP, so we can be able to upload everyone's attendance such a beautiful manner so that everyone will get the participation certificate from AICT ATAL FDP. Please, please, please make yourself available between this 6 to 9 p.m. In the weekdays, and on Saturday from 2 to 8 p.m. So thank you um, for attending, both sessions of today's, and I wish everyone a very, very good night. And once before going to end, I'm just requesting one thing. Just I want to take again 2 to 3 minutes from you participants so that you can put on your camera so that we can take a screenshot before, stop recording. Thank you so much, participants. You can um, turn off your camera, and I wish you very good night, and stay well, stay blessed, and let's meet tomorrow again at 6 p.m. sharp. Thank you so much.